Okay, I think we should start. Hello, good afternoon, everyone. I think today all the participants are from the European countries. So, probably because it's often times of might be less people than we are expecting. Thank you very much for your time to participate in this webinar, and we are very happy to have Dr. Jorge Leandro, who is going to deliver this talk to us. And so, as usual, we will have about 20 minutes for presentation and 10 minutes for discussion. And so, George, the floor is yours.
Thank you, Albert, for introducing me. As I'm aware, this is being recorded, so it will be listened also by other people. This is these Urban Flood Modeling Risk and Management seminars, which is a working group of AIHR, HWA, from the Joint Committee of Hydroinformatics for Urban Flood Modeling and Risk Management. And the talk of today will be on uncertainty chain in forecasts, and I'll be presenting a case study which we use, which is the Oberen Main catchment in Bayern. This is interesting in a way that is following a bit the talk that we had last week with Josep Arónica, so you will find some similarities between the two works. The work I'm presenting is part of a research project, which is a bilateral research collaboration for civil safety between Germany and India. It's sponsored by the Bundesministerium for Bildung and Forschung, and it follows up the June 2013 flood events widespread in Germany and other eastern neighboring countries. As well as some countries, also some places in India. These flood events, they highlighted that these issues are not only to do with high waters, it has to do also with buildings and other infrastructures such as transports, which get affected during flood events. So the aim actually of this project is to develop efficient management tools for flood prediction of medium-sized catchment areas. The idea is that we can produce better flood warnings and faster, which are more reliable than the conventional methods that we have presented and developed so far. I would like now to give you an overview of the partners who are taking part in this project, this FloodEvac project. We have first one, the University Bundeswehr from Munich, which is actually the university who is leading this project. This is led then by Professor Norbert Gebeken, and they are mostly interested in assessing the resistance of bridges. So they are mostly interested in this type of structures. Then there are some other universities which are all then working on evacuation, robust evacuation, like the University of Kaiserslautern, which you see here somewhere in the middle. Then we have also some partners of India, because this is a international, a bilateral cooperation between the two countries. And then you have at Amerita, you will have Professor Hamesh, who is basically working on management of flooding using crowdsourcing. And then we also have a partner from the IIT Delhi, who is mainly responsible for drainage systems. Here at Munich, we are, as we said, we are interested on the flood warning system, and the work package, they are then split in 8, as you can see here on the left-hand side of the graph. And you will see that basically you always have this word uncertainty coming up on these work packages, because the idea is that we can, or we want to estimate the several sources of uncertainty. And at the end, then to produce a web application which can be used for flood warning. And on the right-hand side, you see our team. So we are 6 engaged colleagues. So I'd like to show you the concept that we are implementing. So the idea is that we want to come up with an uncertainty chain which can be fed into forecasts. You all know this picture is basically the global water cycle, which you will always hear when you're doing hydrology in basic level. So basically we have water being evaporated through sun, through the energy of the sun, which then gets transported with the clouds. Eventually it precipitates if temperature goes down, or if you have some orographic factors and so on. And this water will then precipitate into the river, which is basically a network of channels, which will transport the water further downstream into the oceans. Eventually you may have also groundwater, because water will also infiltrate along the catchment, and this water can then feed up aquifers, and it can be also translated laterally as surface water. The issue is if we are interested in forecasting flooding, it's very important that we know the start point. So it is very different if we have a very saturated soil, in which case the rainfall will be directly translated into runoff, or if we have a soil which is dry and the first rains will actually infiltrate and will not generate any sort of runoff. So this sort of complexity needs to be captured if we want to be able to predict accurately our forecasts. And that's why it's important to show this picture, to realize that if we are forecasting floodings for a city, we actually need to consider the whole water cycle. And the way we are doing it in FloodEvac is that we came up with a tool which is being developed in MATLAB. This tool, when ready, it's our aim to make it open so that people also can, after the project is finished, they can also improve it and work on it. And the way it is done, it is split then in 3 parts. So you have a very first one, which deals with the part of the water cycle which is to do with rainfall. And this is the part where we will be dealing then with rainfall uncertainty. Then there is a middle section which is dealing with the rainfall runoff process. And here we will be interested in characterizing the uncertainty of these rainfall runoff models and processes. It then goes into a last section, a third section, and this section is responsible for conveying the water along the channels, and basically everything has to do with overland flow, which cannot be characterized simply by using a rainfall runoff model. And that's why in this section we are using hydrodynamic models. And as you can see, it starts with some simpler one-dimensional runoff hydrodynamic models, and it goes up to more complex models. I want to show you an overview of the type of outputs that we get, and then we'll go into detail into each of them. So as we said, the first section is dedicated to rainfall uncertainty, and we are looking into producing some maps which can actually characterize how rainfall is spatially uncertain. Then we go into the second part, the part which is to do with a rainfall runoff model. And here, as we said, we want to capture, for instance, a whole year of rainfall runoff, such that once we want to do a specific rainfall, a flood forecast in a specific point, we have a model which can tell us what are the initial conditions at that instant in time. We then go to the third part with the aerodynamic modeling, and here we go one step further of the usual flood maps, because we believe that it's better to actually describe the uncertainty that we have also on these flood maps, and not assume that they are unique. So the area which I'm going to show the examples, how we apply this FloodEvac tool, is the Oberen Main catchment, and basically this is a medium-large catchment because it has about 4,000 square kilometers, and as you can see, the range of heights change from 1,000 to 0 meters. So that means that we have a complex source of water, because we can have flooding due to extreme rainfall events, but they can also come from snow melt, or they can have a combination with, for instance, fluvial flooding. So if we are interested in prescribing a forecasting tool, we have to be able to deal with all these types of sources of flooding. In this particular case, we are mostly interested in this city Kulmbach, because it's a city which has in the past had some severe flooding episodes, and actually the city of Kulmbach is very engaged in proactive measures against flooding and other type of management activities, and so this is an ideal case study for showing our tool. So if we go now a bit more in detail into what is being done in the rainfall uncertainty section, we are applying a method which is called turning band methods, which was developed already in 1982. But this method is quite interesting because it allows us, as you can see on the first left picture, it allows us to extrapolate or to estimate what is the rainfall outside the rainfall rain gauges, which you can see here marked with triangles. This is also interesting because what the turning band method does is that it produces several rainfall fields which are all likely to have happened. So you can get 100 different rainfall fields which will all have the same average precipitation. If you then look into these individual 100 realizations, you realize that if we are looking at the points where the rain gauges are, then you don't have any difference between the several realizations. But once you start moving away from the rain gauges, uncertainty starts to increase. And this is basically what is being shown here on the graph in the middle. As you can see, rainfall uncertainty, or a difference between the maximum and minimum realizations, it can go up to 1 millimeter per hour in a field where we have a maximum of 4 millimeters per hour. Again, this can be done then using some quantiles to specify confidence ranges. We go then into assessing the uncertainty of our rainfall runoff model, and here we are using a LARSI model, which stands for Large Area Runoff Simulation Model. This is a hydrological conceptual model because it conceptualizes the processes that can be found in a catchment. Here, for instance, it is possible to split the runoff into two components, one which is called the direct discharge component, which is a fast response component, and then there is a second slower direct component, which are the two of them they add to be the surface runoff. It's then possible also to include two other components. One is the lateral flow or interflow, which is happening on the upper layer of the soil, and then there is the basis the ground discharge, which is happening at the groundwater level. The advantage of this model is that you can replicate all these four components dependently of each other, such that you can better predict your initial conditions when you're wanting to deliver a forecast. And the way then we look into the uncertainty of this model is through the usual Monte Carlo simulations, where we try various combination of parameters within a specified range. This is a output result where you can see the dotted black lines are the observed. The blue dotted lines is the model that we have, model results that we have. Actually, I have to say this model was delivered by the Landesamt für Umwelt, which is the model that they are currently using for forecasts. And then we add on top of it the red band, which are basically the uncertainty of those forecasts. As we can see, we can in acceptable range we can predict the forecasts, the observed events to be within this band. Okay, we then go to the flood extents, and as we said, we want here to go one step further, and we want to actually include the uncertainty in those flood extents. At the moment, this is being shown for 2D flood extents. We want then later on to extend these to also to coupled models, such that we can also include the influence of the sewer network. In any case, what you see here is two different time steps, and as you can see, the flood extents, they change with time, and more importantly, the uncertainty of these flood extents also change. So it's not possible to, with a single map, to actually predict what sort of certainty of uncertainty I have in those flood extents. The outlook, because we are 1.5 years into this project, and we are still 1 year to go. And what we want is to be able to forecast maps, which will be hourly updated and will be put on the WebGIS interface for then taking action in what we've spoken at the beginning with the bridges, if they are safe or not to pass, and also with the evacuation routes that we need to use as a forecast. And this we want to do it hourly. And that's why what we've decided to do was to store a large amount of possible or likely flood extents, and then depending on what the rainfall runoff model is forecasting for the next 1, 2, and 3 hours, we will look for the most similar event that we have stored in our database, and we will use it for use it as a forecast. At the end, it's our objective that this methodology is also applied in India. And I guess I come to the conclusion of my presentation. So I'm happy to take any questions you might have. Thank you.
Okay, thank you very much, George. Any question from the audience?
How do I see the?
Hi, Jorge. Hi, Albert.
Hello, Joe.
Do you mind if I just arrived a little bit late? Do you mind
no
if
problem.
I put just a question in the plot with the forecasts with the hydrographs? At the beginning, it looks like the model data were a little bit out of the uncertainty bands. Where if we go further with the simulation, they look more within these boundaries. Any reason for that, or just question of the data?
It's well, forecasting is quite a hard task. No, it's not something that one takes very light. But this was a section that we selected from the runs we've done, where we had a mixed response, where we did not only had very good results, and where we did not only had very bad results. It was a mix. It's hard to forecast because we have a lot of uncertainty coming in from rainfall, which is actually the largest source of uncertainty, and that uncertainty of rainfall could actually explain some of the differences we see here. However, in this case here, we are just actually showing the rainfall, the uncertainty for coming from the rainfall runoff model. So this is only uncertainty of the parameters in the model. So we are not looking to the rainfall uncertainty, which would likely then help our results to capture also this uncertainty that we see here.
Okay, good. Thanks. My question was more related to at the beginning. So I would expect that the black dots would be within the boundaries, closer than later in the simulation. And I see the opposite. That was, or maybe I'm not understanding the plot correctly.
No, I think you're
because the uncertainties would, I think, increase with time. But I don't see it here as well. So
okay, the reason why we don't see uncertainty increasing with time is because in this example we are only plotting uncertainty stemming from the model.
Okay. Yeah. Okay.
Yes, and the model uncertainty is not constant, but it's something that doesn't increase with time.
Okay. So fine, I understand now. Thanks.
Thank you for the good question.
Do we have more questions?
Yeah, I think I'll ask a question to Jorge. It's Julian from XP Solution. So thanks, Jorge, and thanks, Albert, first for the presentation. What I was wondering is what differs in your general approach from other previous works using Monte Carlo, because there's been a number of other works on the same topic. Yeah, can you tell me a bit more on that?
So, as I spoke at the beginning, this is a tool which we are developing, which is including rainfall uncertainty, and then we are including rainfall runoff uncertainty, and then we are including also the uncertainty that we have from 2D simulations. If you look individually to every contribution, you will find that most of it has already been done in the literature. The novelty that we are trying to bring here is the combination of all of them. So in here, then how we do the uncertainty of the rainfall runoff model is based on the Monte Carlo simulation, and that we will find something similar done on the literature. It's the combination of all these sources which is the novelty here.
Okay, thanks for your answer, Jorge.
Thank you for the question.
Do we have more questions? If not, I cannot ask some questions. First, George, you mentioned about this rainfall uncertainty a lot. Then,
yes.
could you further explain when you combine this information, do you consider you show that the spatial variation of spatial uncertainty, but how did you consider the temporal uncertainty?
Yes, that's a good question, Albert. At the moment, we are not considering temporal uncertainty of rainfall. We are just considering the spatial uncertainty of rainfall. There are some works which they included on the turning band methods, also the ability to account with temporal rainfall uncertainty, and it came out that the percentage of uncertainty stemming from temporal was much less than the spatial one. And that's why we've decided at this stage to leave it out.
Okay, but I might have different opinion because the temporal might give much more influence on this result because the time of concentration of the catchment, they will change the result significantly.
Yes, if you look at these plots, they are actually quite interesting. And let's look at the middle one. The middle one is showing that if we are, spatially speaking, if we are at the rain gauges, our uncertainty is, we assume it to be in existence because it's being measured at that point. And once we move away from the rain gauge, the uncertainty increases a lot, and it can go up to, in this case, up to 1 millimeter per hour. And if you compare on the left-hand side, we had 4. So it's already a large contribution to that uncertainty.
Okay.
But like I said, the people who already investigated this issue using the turning band methods, they came to the conclusion that the contribution from that temporal variation in comparison with what we've seen here of spatial variability was significantly less.
Okay.
And that was the reason why. Yeah.
Yeah. Do we have questions from other audience? If not, can I just ask another one that's about the modeling? So the 1D, 2D model, we had experience for using MATLAB to run the hydraulic model. So did you run that in MATLAB or?
So, okay. Well, actually, this tool is developed in MATLAB, but what the tool is doing is manipulating the data, changing the data for rainfall uncertainties, for rainfall runoff uncertainties, and so on. But the models itself, they are not written in MATLAB.
Okay.
The models itself are for instance, LARSIM is written in Fortran. So they are not run in MATLAB.
Okay, I got it. So you are using MATLAB to control the procedure, but the code, the executable files themselves are in different language.
Yes, exactly. They are different languages.
Thank you. Okay.
May I ask something else?
Yeah.
Regarding this slide, George, you talked about floods from fluvial floods from rivers, coincidental with rainfall, and the use of 1D, 2D models. Just a general question, it's not about this work. What would be, in terms of volume of the water, what will be the impact of the sewer system compared to the to the huge amount of water coming from the river? So my question could be summarized like, do you expect a big impact of the sewer system in this case?
Okay. Well, actually, I had with Albert at 2008, I think, we wrote an article about combined pluvial and rainfall sources of flooding. And what happens is if you have the river levels, which are quite high, then all the water that should be drained by the sewer system, they won't be drained anymore. And if the sewer system has no drainage capacity, even if you have a small rainfall on the surface, it will provoke or will cause some flooding. So that is one situation where you should consider the influence of the drainage system. the other one, of course, if your main flooding is due to fluvial flooding, and the amount of water coming is obviously very, very large, then your drainage system will start losing a role on the flooding. But again, this tool is supposed to be able to handle different types of flooding. Mm-hmm. So we need to have actually to be able to cover all of them, because in case they occur, we have the right model to deal with it.
Yeah, okay. Thanks, George, for that. I was asking this because, well, I missed the first few minutes of your presentation, and I just got that one of the goals of the project is to look for issues with bridges, which I assume mostly go over rivers, and that was the reason.
Yes, that's because the project is also including other partners which are specifically looking at bridges.
Okay.
And of course, at that point, what we are doing, we are looking at the velocities and water depths around the bridges, and we are supplying this information to them. And then they look and see if the bridges are at risk of collapsing or not.
Yeah. Okay, that understood. So that was I was asking about this significance of a pluvial flood for this.
Yes, at that. For the bridges, it would be negligible, of course. Yeah. But for the buildings safety,
definitely, yes,
we have to include them.
Yeah. Okay, thanks a lot. Good project and good presentation. Well done.
Okay, do we have a final question?
Yeah.
Hi, I would like to ask a question. My name is Katya from University of Exeter. I was wondering, how do you combine the uncertainty from the different sources, and whether all of the plausible features are independent?
Sorry, Nina, so this is a question for me or for Exeter?
Yeah, it's for you, George. I'm sorry, I didn't specify.
Let me just go a bit forward. So this is the type of uncertainties that we, with this tool, are aiming to combine. The tool as it is now possible to look at them in a chain way. That is, we can start with rainfall uncertainty, and from the uncertainty we get on this first section, we can carry it on to the second section, which is the rainfall runoff, and eventually to the hydrodynamic part. But this whole chain, we don't have any results yet to present, and that's why you haven't seen them here. But this is something that should come up on the next months.
And may I just add another question? So, I mean, if you, for example, have, let's say, 10 scenarios of rainfall uncertainty, and then you have 5 scenarios of rainfall runoff uncertainty, and let's say other 5. So would you consider each of them independently, or you will try to put more weight into some of them because they might occur? It will be more realistic if they occur in, let's say, clusters.
Well, that's definitely interesting question. At the moment, we are interested simply in the outcome on this part here, because our aim is at the end to have a list of likely to occur events, which we will then look at what is happening at the forecast time and try to pick up the most likely map. So the idea of this structure is actually to be able to produce all this variety of maps. But we are not looking at the likelihood of them.
I see. All right, thank you.
Thank you for your question.
Okay, thank you very much, George, and all the audience for these excellent questions.
So thank you very much for your questions.
I think I have to draw this to a conclusion, and then I would like to thank you again for everyone who participated this webinar. And if you want to recap this you can find out recording on YouTube channel, including the previous events. And I'm also welcoming anyone who is interested to give a talk. Please contact me we can organize some opportunity for you to talk about this. And the other thing that I would like to say is that Qihua and I, we are discussing about to prepare some special session for the coming conference. For example, hydroinformatics in next year, or IHR, European Congress. And so anyone who has some ideas, so what kind of topic or what kind of activity we would like to provide during this conference, please contact us and keep in touch, and let's talk about this. Okay, so that's all. And the next webinar will be the 10th of July. Probably we will move the time slightly later, so to allow the colleagues from the American side can join us more easily. So I will circulate the information very soon. Thank you very much. Thank you and goodbye.
Thank you.